Today we're going to be learning about the tools and different ways that we can measure water quality for our engineering challenge with water filtration. So we're going to be learning about all the tools so that when we build the water filters, you are ready to go to start testing the water. Let's get started. So the first thing we want to clarify is what is water quality and why is it important? So measuring water quality is equal to testing the water's ability to support life on Earth. It's important because without these tests, we won't know if the water is harmful to us or to other organisms. So it's very important that we take some water samples before we drink them or put them into our bodies. So review of our criteria. So remember, our goal is to reach these four things, and these are the standards set by the EPA or the Environmental Protection Agency. So we want the conductivity to be 0, the total dissolved solids to be under 500, pH within the range of 6.5 to 8.5, and turbidity less than 6 NTUs. So in the presentation today, I'm going to be giving you a definition of all of these things. So let's first start with conductivity. Before we do that, we need to clarify this one vocabulary word that's going to be very important to understand these vocabulary words. So dissolving. So to dissolve means to break apart in water. You can see in this picture there's an Alka-Seltzer that's dissolving in water. This solid, when it goes into the water, it will break apart into smaller particles. That's what it means to dissolve. So when we talk about dissolved contents in water, dissolved contents means all the atoms, minerals, and other molecules that are floating around in the water because it dissolved. So when we measure water quality, we are measuring the dissolved contents of the water. So we're trying to figure out what are the things that are floating around the water, things that we can't really see with our eyes, and we use things like conductivity meters, pH meters, TDS meters, turbidity too. And I'm going to teach you what each of these things are in the presentation. Let's talk about what conductivity is first. So conductivity is how well a material can conduct electricity. Electricity is the movement of negative charges like electrons through a material. So materials that have a lot of loose electrons, which are negative charges around an atom, have high conductivity. So this is a picture of a metal, okay? And if you were to see metal really up close, up to the atomic level, metal is made out of these atoms that are put in place. Like the red dots are the metal atoms and the nucleus, which has a positive charge. Around the atom, we have electrons that are floating around. And metals have this unique ability where these negative charges, these blue dots, are able to move around through the metal atoms really quickly. So because these negative charges are able to move around, you can see with these arrows, it's able to conduct electricity. And that's why a lot of electrical items are made out of metal. So you can see here this battery here, which is made out of metal, and the wires that are made out of metal. They're able to conduct electricity because the electrons are moving around through the wire, through the light bulb, and in this loop here. And so that's why this light is able to turn on. Now, not all materials have this unique feature where all these electrons are floating around. Like paper. Paper does not have this kind of structure. Paper is made out of cellulose fibers that have a structure where these electrons have to stay attached to the molecules and they do not move around. So if you were to attach paper to these wires, it's not going to conduct electricity because there's no moving electrons. And that's why this paper is not turning on this light bulb. So how does conductivity work in water? So when you have things like salts, metals, and acids dissolved in the water, it forms these charges in the water, and those charges can conduct electricity. These charges are called ions. So let's take a look at this diagram here. This is a salt crystal. Okay, pretend this is a cube of salt, and if you look at it really up close, salt is made out of these positive and negative charges. They're all just bunched up together. When you put this salt in water, it's going to dissolve, and these individual charges are going to break apart. These are water molecules. These water molecules are going to come and take these individual particles away, and it's going to surround these particles. These individual negative and positive charges are called ions. So that's another vocabulary word. So if there's a lot of these ions in the water floating around, when you pass electricity through here, these charges can move around. So this water with these ions are able to conduct electricity. So your goal is to try to remove all of these salts and ions out of the water so that it could be pure and it will not conduct electricity. Now let's talk about how we're going to measure this conductivity. We're going to be using a conductivity meter, and we're going to build it out of a multimeter, which is an instrument used to measure electricity. We used this last year for the wind turbine. And we're also going to attach it to a battery. This battery, there's going to be a wire attached to one end, which is going to go in the water. And the other end of the battery is going to be attached to the multimeter here. And then the other wire is going to go into the other side of the water. Now, if this water here has ions, which are floating charges, if there's those floating charges in the water, the water is going to conduct electricity, and the electrons are going to flow from the battery through the water through the other wire, and you're going to see some numbers on this multimeter. Now, if this water does not have any ions, it's not going to conduct any electricity, so the reading will be 0. Your goal for the water filtration is to try to get this water to be 0 conductivity. So the unit of measurement for conductivity is new for you as well. So over here you can see the conductivity of several different types of water. You can see here seawater, which has a lot of salt, as you guys know, has really high conductivity. See right here. And if you keep going down, industrial wastewater is conductive, freshwater streams has some conductivity, drinking water in the United States and tap water have very smaller conductivity, and distilled water, which you can buy in the store, has very, very little conductivity. And so you can see here the unit of measure, it's US per centimeter. That is called Siemens per centimeter. Now, on our multimeters, we don't have this reading here. So we're going to be using another measurement called ampere. So you can see right here, the AM. Ampere is a measure of how many electrons flow through an area over time. And milli is a smaller unit of an ampere. So 1,000 milliamperes equals 1 ampere. So we're going to be measuring in milliamperes. And we want to get it to as close to a 0 MA as possible. Now let's switch gears and talk about total dissolved solids. Total dissolved solids, or TDS, is a measure of the number of all dissolved solids like minerals, ions, chemicals, and metals in a unit of water. In this chart here, you can see the TDS of different kinds of water. So the ideal drinking water will be as close to a 0 TDS as possible. Our average tap water is between 200 and 400. And then you can see here 500 plus is US EPA maximum contamination level. So the EPA has determined that anything above 500 TDS rating is not drinkable. So your goal is to get lower than 500, or at least 500. So TDS is measured in parts per million, or ppm. You might be wondering what that means. ppm means 1 part of a million of something. So for example, let's say this cube is divided into a million parts, okay? This dot right here, one little dot out of the whole million is 1 ppm, or 1 part per million. In water, you can also think of it as how many milligrams of a solid there are in a whole liter of water. A liter is 1,000 milliliters. So how many milligrams in 1,000 milliliters? Like I said, most water bottles and tap water have between 0 to 500 ppm. Your goal is to get to as close to as 500 or lower as possible. So we measure TDS using a TDS meter. So this is a typical TDS meter. What you do is you put this meter into the water and it gives you a reading of how many ppm of solid there are in the water. There are advantages and disadvantages to this though. So the typical TDS meter will only measure charged particles. What I mean by that is like metals, salts, minerals, and food coloring. Charged particles, you can see here. Notice how each of these atoms and molecules here have a positive or negative charge next to them. See, plus, minus, plus, minus. So these TDS meters can only read things like this. It will not read molecules that have no charges. So for example, oils, gasoline, some drugs, and pesticides, they don't have charged atoms or molecules. So they're just going to be floating in the water. And this TDS meter is not going to be able to pick up on these oils or gasoline. So in that way, it's not as accurate as it could be. The only way that we can measure the true TDS of a water that includes all the oils and gasoline and all the charged particles is to evaporate out all the water and weigh and measure and analyze whatever's left behind, which takes a lot of time and a lot of really special equipment. So we're not going to be doing that. We're just going to be using the TDS meter. Just keep in mind it's only going to read the charged particles, okay? Now let's talk about pH. So you may have remembered pH from 6th grade when you did a couple of experiments with your 6th grade teacher. But just as a review, pH is a measure of the number of hydrogen ions. So hydrogen ions are hydrogen atoms that have a positive charge, and it's usually represented by this chemical symbol H+. So you can see here in this picture, here is water and we poured acid on top. This acid will form hydrogen ions. So you can see here this H plus, that represents hydrogen ions that are floating in the water, because when you mix this up, water and acid together, some of the acid, the hydrogen from the acid is going to be floating around like this. Let's look at this a little bit closer because you might be wondering how in the world does an acid become H plus, right? So if we were to look at acid in a really closer level, so let's take vinegar for example. If you look at vinegar, the structure of vinegar looks like this: 2 carbons, 3 hydrogen, 2 oxygen, and a hydrogen attached to an oxygen. So what happens is when you pour vinegar into this water, this hydrogen right here is going to come off because the water is going to take it off. It's going to be attracted to it, and this H is going to come off, and that H ultimately is what's going to make the water more acidic. So because this H came off, the number of H floating around in the water is going to increase, and that's going to contribute to a pH reading, more acidic. So now you know how acids contribute to the number of hydrogen ions. So let's talk about the pH scale. So the way we know how acidic or non-acidic or basic a material is we use a pH scale. It ranges from 0 to 14. So anything that is between 0 and 6 is considered acidic. That means there's a lot of hydrogen ions present in whatever solution it is. And you can see these materials here, like a battery acid, lemon juice, grapefruit juice, coffee, even milk and saliva are acidic. That means it has slightly more hydrogen ions. 7 right here is neutral. Pure water is neutral. That means it is neither acidic nor basic. Anything above 7 here is a base, which means it has very few hydrogen ions and it has more hydroxyl ions, which I will not talk about because that's a more advanced high school things, but just know that if there's fewer hydrogen ions, it's basic. Things like seawater, baking soda, ammonia solution, bleaches, or even drain cleaner. Now we're going to be using a digital pH meter that looks kind of like this TDS meter, except it's for pH. We're going to be putting it in the water like that, and we're going to be getting a pH reading. And your goal for the project is to get between 6.5 to 8.5. Now let's talk about turbidity, finally. So turbidity, this is review from last year, is a reading of how clear the water is and how much light can pass through a sample. Turbidity can be affected by dirt, silt, solids, chemicals, or other pollutants in the water. So you can see here in this picture, the water sample on the left is very, very clear. whereas the water sample on the right has very cloudy water. And so the amount of light that can pass through each of these is very different. This left sample can pass a lot of light through, but this right sample is very cloudy and cannot pass a lot of light through. So let's talk about how we measure turbidity. We can measure turbidity using a clear plastic tube with a Secchi disc at the end. This is a picture of a Secchi disc that's used in rivers and lakes. You can see here, you can't really see the string here, but there's a rope that's attached to the Secchi disc. And how you use it is you would lower it into whatever you wanted to test, like a lake or a stream. So you lower it, and the point where you cannot see the difference between the two colors is actually how you measure turbidity. The clearer the water, the deeper you can go. For our purposes, because we're not going to be working with really large amounts of water, we're going to be using a turbidity tube, which is exactly the same thing, except the Secchi disc is going to be at the bottom of the tube, and you're going to be pouring your filtered water in through here. And you're going to measure how much water you can pour before you can't distinguish between the black and the white here. The higher up you can go, the clearer the water. So if you pour like this much water and you can't see the difference, that means your water is very dirty or it has very high turbidity. So your goal is to get your water as clean as possible. Finally, let's talk about the unit of measure for turbidity. So turbidity is measured by nephelometric turbidity units. You do not need to know this word, just remember NTU. And NTUs, so here's some examples. A very high NTU reading, like this one's 250 NTUs, means that the water is extremely cloudy. The lower the NTU, like this one's 10 NTUs, the cleaner the water. Your goal for the project is going to be to get less than 5 NTUs if possible. Okay, so that's your challenge. And that concludes all the information you need to know to test your water for the project.